Welcome to The Explainer. Today, we are diving deep into a silent, destructive force that's all around us. It weakens our bridges, it crumbles our cars, and it costs the global economy, get this, an estimated $2.5 times trillion every single year. Yep, we're talking about corrosion.
And it all kind of starts with a simple question, right? Why does a metal chain left by the ocean just fall apart in a few months, but the same chain in a dry desert might last for decades? Well, the answer shows us that corrosion isn't some simple one-size-fits-all process. No, it's more like a chemical drama, with a whole cast of characters influencing the final scene.
Okay, so let's get right into it. To understand what's going on, we first need to get a handle on what corrosion actually is. And believe me, it's way more than just some ugly rust on a piece of iron. It's a fundamental process of nature itself.
So here's the key thing to wrap your head around. Corrosion is a completely natural process. Think of it like this. We humans spend enormous amounts of energy to refine metals from raw ore we dig out of the ground. Well, corrosion is just nature's way of trying to turn those shiny, refined metals back into their original, more stable, earthy state. It's basically a slow-motion return to where they came from.
So how does this process actually kick off? It all happens through something called an electrochemical cell. You can honestly just picture a teeny-tiny self-destructing battery that forms right there on the metal's surface. And this little battery needs three things to work. First, an anode. That's the part that actually corrodes by giving away its electrons. Second, a cathode, which is what receives those electrons. And third, and this is crucial, an electrolyte. That's usually just water, and it acts like a highway for everything to flow. Now, if you take away any one of those three things, the whole destructive process just grinds to a halt. But that tiny battery doesn't just operate in a vacuum. The world around it can either slam on the brakes or it can hit the accelerator. So let's take a look at the external environmental factors that can dramatically speed this whole thing up. All right, here are the main environmental players. Moisture is the big one, of course. That's the electrolyte we were just talking about. Then you've got oxygen, which is essential for the chemical reaction to even happen. And then you have the accelerators, temperature, pollutants like salt, and the overall pH, which is basically just how acidic or alkaline the whole environment is. You can think of these as the fuel and oxygen for the corrosion fire. And this chart just shows you how much of a difference the environment can make. I mean, look at this. The corrosion rate of steel in plain fresh water is pretty low. But you put that same steel in salt water, it absolutely skyrockets. And why is that? Well, because all that salt makes the water a much better conductor. It turns it into a supercharged electrolyte. This allows that tiny destructive battery on the metal surface to run way faster and much more efficiently. Air quality plays a massive role too. In clean, dry air, a piece of metal is actually pretty safe. But in a polluted, humid city, it's a completely different story. Pollutants like sulfur dioxide, which you get from industrial emissions or even just traffic, mix with rain or humidity to form weak acids. This so-called acid rain doesn't just damage plants, it aggressively attacks the surfaces of buildings, bridges, and statues, seriously speeding up their decay. And finally, you've got heat. It's just like how warming up a pan helps you cook food faster. Higher temperatures give all the molecules involved in corrosion more energy. And with all that extra energy, the chemical reactions just happen so much more quickly. It's exactly why things always seem to rust faster in warm, humid climates than they do in cold, dry ones. But here's the thing. The environment isn't the whole story, not even close. The properties of the metal itself play a hugely important role. Sometimes the enemy is coming from inside the house. So these are the internal or material factors. It's all about the metal's fundamental identity, what it's made of, how pure it is, its physical condition, and even how it's designed. The metal's own characteristics are every bit as important as the world it's living in. Okay, this brings us to something called the galvanic series, which is a total aha moment for understanding why you can't just bolt any two metals together. See, when different metals are touching and there's an electrolyte present, one will always become the anode, the victim, and the other will be the cathode. So for example, if you connect zinc to steel, the zinc literally sacrifices itself to protect the steel. But if you connect that same piece of steel to copper, the steel now becomes the victim and corrodes to protect the copper. It's a real hierarchy of self-destruction. The purity of the metal is another huge factor. A perfectly pure metal is actually pretty resistant to corrosion. But, as this quote highlights, tiny impurities can act as little cathodes, creating thousands of those tiny corrosion batteries all over the surface. And this leads to really concentrated, rapid pitting and decay from the inside out. And you know what? Even the history of a piece of metal matters. Any areas that have been bent or welded or stressed out are physically different at a microscopic level. They hold more energy, and these high-energy spots become the very first places that corrosion starts to attack. It's exactly why the sharp corner of a bent plate often rusts long before the flat, smooth surface right next to it.
Okay, so we've identified the culprits, right? Both external and internal. The environment attacks from the outside, and the metal's own properties can work against it from the inside. Now that we know the enemy, how do we fight back? Let's look at the strategies.
And this is where all our knowledge translates directly into solutions. See, to stop corrosion, all we have to do is break one of the legs of that electrochemical triangle. Barrier coatings, like a simple can of paint, just physically block moisture and oxygen from ever reaching the metal. Sacrificial coatings, like galvanizing steel with zinc, use that galvanic series to our advantage by providing a different metal that corrodes first. Or we can just be smart and select a better material from the very start, like stainless steel. So the next time you see some rust on a fence or a bridge or an old car, you won't just see decay. You'll see this complex chemical reaction shaped by water, by air, by salt, and by the very nature of the metal itself. And remember, understanding this process is the very first step to controlling it. So how are you going to see the world of metal around you differently now?